Okay, in this video, we're going to talk about buffers. And a buffer is a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid. So they're solutions really that contain both an acid, we'll call this acid HX, and a base, X minus. So both of those things are going to be present in this solution, this beaker of chemicals, if you will. So one of the ways you can think about this is just, well, a weak acid dissociating into its normal equilibrium already creates this conjugate base. And so here's a weak acid. Here's a conjugate base. Now, in a buffer, you need the concentrations of these two things to be high enough, as we'll see, to get some good buffering action. But what we're thinking about here is the act of a buffer to resist changes in pH. And the way it does this is when a little bit of OH minus is added, the acid will react with this OH minus and produce its conjugate base. Or if H plus is added, the conjugate base will react with this and make the acid. Okay, so we'll see this played out with some examples, but that's the general idea of a buffer. Now, the by the book definition is a solution of a weak conjugate acid-base pair, and the point of the buffer, as is written here, is to resist drastic changes in pH. And they're going to be solutions that contain relatively high concentrations of this acid and its conjugate base pair, or a base and its conjugate acid pair. But you want the concentrations to be higher than 10 to the negative 3 molar, usually say 0.1 molar or so, of both the acid and the base. So it can't just be a weak acid that's dissociating by itself in say 0.1 molar of this, because you never get enough of the conjugate base around. So you actually have to make these solutions up with approximately equal concentrations as well of both of these conjugate pairs. Now, the importance of a buffer is that a lot of chemistry will change as the pH changes. Maybe you want to design a drug to be used in a human. So this drug has to enter our bloodstream and maintain its structure and chemical reactivity that you're designing it for. And well, you might know the pH of blood, and it's pretty steady in the human body. And so when you're studying this thing in the laboratory, you're not studying the drug action in blood, you're studying it in a buffer solution. And so you want to study the reaction of that drug in the buffer solution so that the pH is not changing a lot throughout your chemical reactions you're studying, so that you know the activity of the drug is in this blood pH range, and the pH isn't changing a bunch and changing the activity of said drug. So buffers are used quite a bit in biochemical studies. So that's just one area, of course. Now, how a buffer works, we sort of alluded to this earlier, and this probably should say weak base here and conjugate acid. Okay, is that you mix this weak acid and conjugate base pair to make your buffer solution, or your weak base and conjugate acid pair, and now you have a sort of reaction you can think about setting up. Here's your weak acid, here's your conjugate base, right? Or here's your weak base, here's your conjugate acid. Okay, now adding a small amount of acid, as we said before, if we add a little bit of H plus in this solution from some other outside chemistry that's going on, well, this base will react with this H plus to make my conjugate acid. Or if there's some OH minus added here, well, then the acid HA will react with OH minus to make my conjugate base A minus. Okay, so the point is that when you're studying something in a buffer solution, if some new H plus or OH minus comes into the picture, it is sort of neutralized immediately by the acid or base. So if you think about the concentration of the, let's draw it perhaps down here a little bit more, of the acid and base pair, and you start them off relatively equal. So the size of this bar here is maybe the concentration of the acid. And so if you add a little bit of H plus to this, what'll happen? The amount of the base will go down a little bit since it's reacting with this acid. And so the bar then might be adjusted a little bit, and this will go down just a hair to maybe here, as it's reacted a little bit with the H plus that you've added, right? But your concentration of the conjugate base is still pretty high, and it's still pretty much a one-to-one mixture because you want equal concentrations of the acid and the base. So this H plus has been neutralized, and you still have a buffer mixture that's roughly equal amounts of acid and base. And so the pH of the solution hasn't changed. Why? Because you still have equal amounts of the acid and base. And you can have the same sort of scenario, of course, starting off with equal concentrations if you add a little bit of a base. So somewhere in the chemical reactivity, there's an OH minus that's generated. Well, the acid now is going to eat up that OH minus. And so this is going to go down a little bit. And so now you have a little bit less acid, but you still have roughly the same amount of acid to base. And so the pH overall is going to be relatively the same. So that's how a buffer works. The point is to maintain the pH throughout whatever chemical reaction you're trying to study. And so adding a small amount of acid or base only slightly neutralizes one component of the buffer. And so the pH overall doesn't change very much. Now, we have calculations for calculating the pH of a buffer because, look, you're adding acid and base together, but it depends on the strength of these two to determine the overall pH of this. Just because they're equal amounts doesn't mean they completely neutralize and make a pH of 7. So we have equations for calculating the pH of a buffer. And we know that it's a weak acid, so there's a weak acid dissociation constant. And we can do some basic algebra, taking the negative log of each side and using a property of logs over on this side, right? Negative log of H plus times A minus over HA. When you multiply logs, right? Log of X, Y over Z, right? I can say is the same as log of X, right? Plus log of Y over Z. Or I can say the negative log of X plus negative log of Y over Z. And that's basically what I'm saying here. I'm taking the negative log of both sides. So I have negative log of Ka. We call that, of course, the pKa. And I have negative log H plus as a result. We call that, of course, pH. And so after some basic rearrangement, after taking the negative log, I have this down here, which I'm going to call the Henderson Hasselbalch equation. And this is the equation we're going to use for calculating the pH of a buffer, right? And of course, what we need to know is, well, what acid are you using and what is the Ka? So I can calculate this. And then, of course, what is the concentration of the conjugate base that you're mixing with this acid? So sometimes you'll see this written as pH equals pKa plus log concentration of base over concentration of acid. Okay. Again, you want these numbers to be relatively equal so that the amount of the acid and base is relatively equal, and you want them to be substantial, like 0.01 molar, 0.001 molar, 0.1 molar, 1 molar, something like that. Just not 10 to the negative 5 molar, right? You need to have enough of this acid and base around so that when there becomes a little acid or base added to the mixture, it can neutralize it without really eating into the amount of total base or acid. So that's the Henderson Hasselbalch equation. We can see how we can actually apply this. One note here is that technically, right, these concentrations here, since they're derived from these concentrations, technically these should be the equilibrium values, right? Where you'd have to do an ice chart and worry about all the changes and then get the equilibrium values. But most of the time, since these are weak acids, there's very small dissociations, neglecting X is safe. Usually this is going to be fine to just, if Ka is small, so if Ka is small, then neglecting X is probably fine. And this ratio can use initial concentrations. Okay? And the point of me saying this is that usually in a problem or in a laboratory, you're going to be, saying, all right, well, what happens if I mix 0.4 molar of base with 0.5 molar of acid? Those are the initial concentrations that you're mixing together. Those are usually fine to put in here as long as it's a weak acid and weak base pair. Okay? All right. Now, let's look at a problem here. What is the pH of a buffer that is 0.12 molar in lactic acid? So that's what you're grabbing this bottle of lactic acid off the shelf, 0.12 molar, and you're mixing that with 0.1 molar sodium lactate, right? Notice this is the lactate ion. This is a strong electrolyte. So this is going to be your conjugate base, this lactate ion, to this weak acid, lactic acid. And here you're given the Ka for lactic acid. So all you do here, pH is pKa log of base over acid. You put in the Ka value, take the negative log of it to get your pKa, and then it's plus log of the base. So just make sure you're identifying here acid 0.12, right? So that's my acid that goes in the denominator. The base here, sodium lactate 0.10, that goes in my numerator, and that's why I have them 0.10 over 0.12. So you enter all this into your calculator. Negative log of 1.4 times 10 to the negative 4 is 3.85. Log of 0.1 over 0.12 is negative 0.08. You add these two things together, and the pH here is 3.77. So even though there's relatively similar amounts of acid and base here, and it's actually, a little bit more acid than the base, the pH is still pretty low of this buffer. But there's significant portions of the acid and the base mixed together there that it's going to be able to neutralize any acid or base and not change its pH too much. Okay, so that's one example. Let's go into a practice problem and really apply this to calculating the pH from a Henderson Hasselbalch equation, and then calculating it a separate way, making no assumptions about being able to use the Henderson Hasselbalch. So calculate the pH of a buffer that initially contains 1 times 10 to the negative 3 molar of CH3COOH and 1 times 10 to the negative 4 molar CH3COONA. So acetic acid and sodium acetate. First, we're going to use the Henderson Hasselbalch equation. So we know the Henderson Hasselbalch equation here, pH. We've just used it, of course, pKa plus log base over acid. Concentration. Okay, and maybe I'll write here in blue since I've been using that. Base over acid. The base here, reading through CH3COOH, that looks like my acid. This thing with sodium is the strong electrolyte, so this is my base. So this is going to be the number here. That becomes my base number. And this other number is going to be the number I use for my acid. 1 times 10 to the negative 3. That goes in down here. For pKa, well, I have the Ka written here, so this means I'm taking the negative log of this 1.8 times 10 to the negative 5. And that's what's going to become my pKa. Okay. All that said, I can calculate this. So this is step 1 here. Using Henderson Hasselbalch, pH is going to be negative log of this Ka value, 1.80 times 10 to the negative 5, plus log base over acid. So this 1 times 10 to the negative 4 molar over 1 times 10 to the negative 3 molar. And doing all this, I should get a pH of, for the first part, pKa 4.74 minus 1. So my final pH here, calculating all this out, is 3.74. Okay, that is part 1 here. Part 2, making no assumptions about any of the quantities here. So we're going to use the quadratic formula. How would we do this? Well, we know we better get a nice chart involved. So let's write the reaction here, CH3, COOH. This is an equilibrium, right? It makes H plus and CH3, COO minus. Now I make my ice chart. And this is kind of like the common ion, right? Where there's already a concentration of the acetate around. So the acid initial concentration is 1 times 10 to the negative 3 molar. The H plus is 0. But the sodium acetate, the conjugate base here, is already in the solution. And that's 1 times 10 to the negative 4 molar from our problem. Since H plus is 0, it has to go up. And so all the products, since they're 1-to-1 stoichiometries, will also go up, and the reactant will go down. And so my equilibrium mixture is 1 times 10 to the negative 3 minus x. This is x. This is 10 to the negative 4, 1 times 10 to the negative 4 plus x. And so we have my Ka value, 1.8 times 10 to the negative 5, equals x, 10 to the negative 4 plus x, that's the products, over reactants, 10 to the minus 3 minus x. Okay, I was told here, don't assume anything, make no assumptions, right? Usually we would neglect x's here, but we're told not to neglect the x's here. And if we do, it wouldn't pass our 5% rule anyways. So we're going to have to rearrange all of this and use the quadratic formula. Ugh, I know. So if you multiply both sides of the equation by this denominator so that you get 10 to the negative 3 up on this side, and it's away here, and you distribute this x, you can get something that looks like 1.8 times 10 to the negative 8 minus 1.8 times 10 to the negative 5x on the left equals 1 times 10 to the negative 4x plus x squared on the right. And we know if we want this in quadratic notation, we want to get 0 on one side. So we can collect everything over to this side and come up with the following. 0 is x squared plus 1.18 times 10 to the negative 4x minus 1.8 times 10 to the negative 8. And so for the quadratic formula, I need these a, b, and c values. A is right here. The coefficient before x squared, so it's 1. My b value is right here. And my c value with the negative sign here is negative 1.8 times 10 to the negative 8. So my x here is opposite to b plus or minus the square root of b squared minus 4ac all over 2a. And so I put in my a, b, and c. I'm going to get two different values because there's a plus and a minus here. And those two values I get at the end are the following: 8.76 times 10 to the negative 5, or negative 2.1 times 10 to the negative 4. So when I use the quadratic formula, I know I'm going to get two values out at the end, and one of them is going to make sense, one isn't. So what does x represent? X represents the amount of H plus at equilibrium. Can we have a negative concentration of H plus? No. So this x can't be negative here. So we know this one must be wrong. And so the one we want, the x value we want, is here. And so calculating the pH, it's negative log of this number. Negative log 8.76 times 10 to the negative 5. And that gives me a pH of 4.06. So returning here, without any assumptions, it's 4.06 is the pH, which is, 10% or so different than what the Henderson Hasselbalch tells us. Usually the Henderson Hasselbalch will be a very good approximation of going through the full quadratic formula. Here it is not, okay? And I'll tell you why. The Henderson Hasselbalch equation will fail if the initial concentrations are small, right? And here they're pretty small, right? 10 to the negative 4 molar is really tiny, okay? For Henderson Hasselbalch to really be a good approximation, right? If maybe I'll write this a different way. Henderson Hasselbalch will fail and be a poor approximation the initial concentrations of the conjugate acid and base pair are small and only maybe 10 to 100 times as large as Ka. Okay, so these are pretty small concentrations, and if Ka is times 10 to the negative 5, and my initial concentration is only 10 to the negative 4 or 10 to the negative 3, that's not going to be high enough to make Henderson-Hasselbalch equation a good approach. Okay, so I wanted to show you one example here of one example, I should say, where Henderson-Hasselbalch fails, but we can compare the pH. Even when it fails, it's off by 10%. But remember, pH is a logarithmic scale, so although these two numbers are not that different, it's a pretty big difference in the amount of H plus for instance 1 and instance 2. So, in this lecture, we introduced the concept of buffers and showed you how to calculate the pH of a buffer. Moving forward, we'll worry about how we can then calculate changes in buffer pH when we add an acid or a base to this buffer solution, and continue our track towards learning how to calculate titrations and changes in pH for a titration of a weak acid and strong base, or weak base and strong acid. But that's coming up in future lectures. So that'll do it for this lecture. See you next time.